Okay, so in this video we will be doing the first lecture on the estimation methods or point estimation in statistics. Okay, so first of all we will explain and define the estimation. Okay, so in statistics, actually estimation is one of the widely used method to predict or estimate the value of a certain population parameter. Okay, so estimation is actually getting the value of certain population parameter like mean, mu, okay, using some sample statistics. Okay, this sample statistics may be X bar. Okay, so estimation is actually getting the value, or we can say that predicting, okay, or estimating the value of certain population parameter, okay, like the mean of a population, mu, using some of the sample statistics like X bar, which is the mean of the sample. Okay, so now in estimation we have two types of estimation that is done in statistics. Okay, the first one is the point estimation and the second one is interval estimation. Okay, we will be focusing on this first one, the point estimation. Okay, but I will explain the difference between these two. Okay, so point estimation, actually it predicts or it estimates a certain value. Okay, it estimates a certain value, okay, single value, okay, for a population parameter using the sample statistics. Okay, while the interval estimation, it estimates the range of values, okay, of certain population parameter using sample statistics. Okay, both are similar methods, but in point estimation we get a single value, but in interval estimation we get a range of values. Okay, by interval estimation, okay, the best example is the confidence interval. Okay, confidence interval, which is a value of, like, we say X bar plus minus standard deviation, okay, divided by under the root n. Okay, now this plus minus, it gives us certain range, like for example from 100 to 200. So the best estimate is that the population parameter falls between 100 and 200. Okay, so this is how the interval estimation works. But in the point estimation we get a single value for a population parameter. Okay, for example, I am considering the mean of a certain population, okay, which is mu, and I want to find or estimate the mu using the X bar for a sample that is taken from this population. Okay, so the range of values. Okay, by interval estimation, okay, the best example is the confidence interval, okay, confidence interval, which is a value of, like, we say x bar plus minus standard deviation, okay, divided by under the root n. Okay, now this plus minus, it gives us certain range, like for example from 100 to 200. So the best estimate is that the population parameter falls between 100 and 200. Okay, so this is how the interval estimation works. But in the point estimation, we get a single value for a population parameter. Okay, for example, I am considering the mean of a certain population, okay, which is mu, and I want to find or estimate the mu using the x bar for a sample that is taken from this population. Okay, so the expected value of this x bar, I consider it as mu, which is the mean of the population. So using a small sample, actually, I predicted or estimated the value of a certain parameter, okay, of a large population. Okay, this large population value cannot be easily determined because it requires a rigorous kind of, work and rigorous time, actually, which is not possible for a statistician. Okay, so what statisticians do, okay, they use the sample data. Okay, now I will explain, the sample statistics, population and sample data. Okay, so this thing works in this way. Okay, so we have a large population, consider it as a large population. For example, large population, for example, world population. Okay, this is the world population, okay, which is maybe around like 6 or 7 billion people. Okay, and we want to find actually that what is the average height of men around the world. Okay, so literally we cannot do the calculation, or we cannot measure the average height of each person, the height of each person in the world, and then take the average of that. Okay, so what we do is we use sample data to predict this or estimate this. We use the sample data. Now what is that sample data? This is like, we have, like, for example, 100 men from Pakistan, okay, 100 men from Saudi Arabia, 100 men from for example Qatar, okay, 100 men from, like, each country. We have like a sample data of 100 men from each respective country. So it makes us like the data for, like, for example, only like 18,000 people, for example. Okay, so now what we do is we collect the data of only 18,000 people. We calculate the average x bar for this sample data, and we estimate it. We predict that this x bar actually represents the average height of this population of 6 or 7 billion people. Okay, so that is how this estimation actually works. So what we do is we use the sample data, which is a smaller data. Okay, we calculate certain parameter for the sample data, and we equate it to the population parameter. Okay, so that is how we do the point estimation. Okay, So in point estimation, we have like the sample statistics being used, okay? Sample statistics being used to estimate the population parameters. Okay, so these sample statistics are actually point estimators, okay? Point estimators. Okay, and the output that it gives, the output or the single value that it gives are estimates. Point estimates are estimations. These are point estimates. Okay, these point estimators actually are random variables, okay? Random variables, and it is quite important to look for the distribution it follows, okay, to get the correct point estimates. Okay, so the distribution of these point estimators actually, you know, they have quite a role in estimating the best value. Okay, because without the distribution, if we don't know about distribution, we cannot predict the exact value. Okay, so the sampling distribution is very important to find the best estimate. Okay, now we have certain properties of these estimators, or properties of point estimators. The number one property is unbiasedness. Okay, the second property is the minimum variance. I will explain one by one and do some examples on it. Okay, so the third one is efficiency. The fourth one property is consistency. The fifth property is sufficiency. And the sixth property is robustness. Okay, so these are the 6 properties of these point estimators. Okay, so let's do the first one, the first property, which is the unbiasedness. Okay, the unbiasedness means that if the estimated value of certain parameter, sample parameter, is equal to the population parameter, okay, then this sample estimator, or we can say sample statistics, theta bar, is unbiased estimator. Okay, because for all values of this we get the exact same theta. Okay, or we can say that on average the estimator should give So the third one is efficiency. The fourth one property is consistency. The fifth property is sufficiency. And the sixth property is robustness. Okay, so these are the 6 properties of these point estimators. Okay, so let's do the first one, the first property, which is the unbiasedness. Okay, the unbiasedness means that if the estimated value of certain parameter, sample parameter, is equal to the population parameter, okay, then this sample estimator, or we can say sample statistics, theta bar, is unbiased estimator. Okay, because for all values of this we get the exact same theta. Okay, or we can say that on average the estimator should give the value equal to population parameter, which is theta. Okay, we know that there is always some variations. Okay, nothing is perfect. Okay, and there is no perfect estimator actually to give us the perfect value or the right answer. Okay, but we should have an estimator that should do at least that the average or the expected value is equal to the parameter that we want to find, or we are supposed to estimate it. Okay, so on average, okay, this sample parameter should give us the population parameter. Okay, so this property, that for each value of this sample parameter we are getting the theta, which is the population parameter, is unbiasedness or unbiased estimator. Okay, so by definition, if I define it exactly, okay, so unbiased estimator is a statistic, okay, theta bar, okay, by bar it means that it is a sample statistics. Okay, theta bar is an unbiased estimator of parameter theta of a given distribution if and only if the estimated value of this theta bar is equal to theta for all possible values of theta. Okay, so let's do an example on it to show that whether a estimator is biased or unbiased. Okay, I will do the example in the next video. We are doing the example 1, that is on page number, let me see, 284. Okay, page number 284, example 1. Okay, and it says that, let me narrate it, that definition 2, okay, which is the definition of the unbiased estimator, requires that E of this sample estimator is equal to theta, which is the population parameter, for all possible values of theta. Okay, so to illustrate this statement, it is necessary show that unless theta is equal to 1 over 2, okay, the minimax estimator, okay, and estimator is equal to x plus 1 over 2 under the root n divided by n plus under the root n. Okay, this is the minimax estimator. Okay, show that this estimator, okay, is biased. Okay, so let's solve this. Okay, so we know that x is following a binomial distribution with the parameters n and theta, where n is the number of events and theta is the probability of success. Okay, so E of x actually is equal to n theta in binomial distribution. That is what we know. Okay, now we know that the estimator theta bar is equal to x plus 1 over 2 under the root n divided by n plus under the root n. So the estimated value of this estimator, it should be equal to theta. Okay, if it is unbiased. Okay, and if it is not equal to theta, then it is biased. So it will be equal to E expected value of x plus, putting this theta bar is equal to this thing. Okay, so it is equal to x plus 1 over 2 under the root n plus under the root n. Okay, so it is equal to e raised power x plus 1 over 2 expected value of under the root n divided by expected value of n plus under the root n. Okay, only this thing is variable x. This is constant and this is constant, so expected value of constant is again the same constant. Okay, so it is equal to E of x plus 1 over 2 under the root n divided by n plus under the root n. Okay, now we know that E of x is equal to n into theta in this binomial distribution as given above. Okay, so putting this value over here, it is equal to n theta plus 1 over 2 under the root n divided by n plus under the root n, and it is the value of this expected value of this. It will be equal to E expected value of x plus, putting this theta bar is equal to this thing. Okay, so it is equal to x plus 1 over 2 under the root n plus under the root n. Okay, so it is equal to e raised power x plus 1 over 2 expected value of under the root n divided by expected value of n plus under the root n. Okay, only this thing is variable x. This is constant and this is constant, so expected value of constant is again the same constant. Okay, so it is equal to E of x plus 1 over 2 under the root n divided by n plus under the root n. Okay, now we know that E of x is equal to n into theta in this binomial distribution as given above. Okay, so putting this value over here, it is equal to n theta plus 1 over 2 under the root n divided by n plus under the root n, and it is the value of this expected value of this estimator. Okay, so in order for this theta bar, that is the estimator, to be unbiased, this should be equal to theta. Okay, so E of theta bar should be equal to theta, but E of theta bar is equal to this value, so equating it to theta, so what we get is n of theta plus 1 over 2 under the root n divided by n plus under the root n is equal to theta. Okay, so it will be equal to n theta plus 1 over 2 under the root n is equal to theta into n plus under the root n. Okay, so now what we do is we can get multiplying this. Okay, so we will get n theta plus theta into under the root n. Now this is n theta and this is n theta, so both will cancel each other out. Okay, and 1 over 2n is equal to theta under the root n. Now under the root n is equal to under the root n, so theta is equal to 1 over 2. So 1 over 2 under the root n is equal to theta under the root n. Okay, so we know that A cross B is equal to C cross D, so A is equal to or we can say C cross B. When A cross B is equal to C cross B, okay, so B and B are same, so A is equal to C. So here 1 over 2 is equal to theta, so theta is equal to 1 over 2. Okay, so when theta is equal to 1 over 2, E of theta bar is equal to theta. So for only the value of theta is equal to 1 over 2, this estimator gives us a value of theta. So it is this estimator, we can say that this estimator is biased. Okay, this is not unbiased, this is biased, because for every value of theta we are not getting the value of E of theta bar is equal to theta. Okay, for only okay, now we will do the example 2, which is on the same page. Okay, and it says that if capital X has binomial distribution, okay, the distribution is given to us. So now we are clear, okay, that it has binomial distribution and the parameters are with parameters n and theta. Okay, where n is the number of events and theta is the probability of success in the respective event. Okay, so that the sample proportion, okay, so that sample proportion which is x by n is unbiased estimator of theta. Okay, so we are given that we have the binomial distribution, so E of theta bar actually is equal to n theta. Okay, now theta bar over here is x by n. This is the what we say sample statistic, okay, estimator. Now the E of theta bar is equal to expected value of x by n. Okay, if it gives us theta, then this is unbiased. If it does not give us theta, then it is biased. So it will be equal to expected value of x multiplied by expected value of 1 over n. Okay, this is constant, so expected value of 1 over n will give us 1 over n and expected value of x. Now we know that the expected value of x is equal to n of theta. So 1 over n into n of theta, n will cancel each other out and it will be equal to theta. So E of theta bar is equal to theta. So this is unbiased estimator. Okay, x by n is unbiased estimator of theta. In this video we will be doing the asymptotically unbiased estimators. Okay, so for this version of unbiased estimator, we first need to understand the concept of bias. Okay, bias, which is denoted by Bn of theta. Okay, for an estimator to be unbiased, we say that Bn of theta is equal to 0. If this thing is equal to 0, then it is totally unbiased estimator. Okay, and by totally unbiased estimator we mean that it hits the center every time. Okay, by hitting the center I mean that it gives the exact value of the parameter of population parameter every time. Okay, so what is bias actually? This bias Bn of theta, actually it is the measure of how far the expected value of an estimator theta bar is from the true population parameter theta. Okay, we know that we use estimator theta, okay, to find the value of the true parameter theta. We use sample data to predict the value of the population parameter. For example, we use the sample mean, okay, x bar, to find the population parameter mu, the mean of the population. Okay, so that sample mean x bar is asymptotically unbiased estimator if if the sample is small. Okay, for small sample size n, okay, for some small sample size n, the estimator E of it does not gives us the exact value, but for n, tending to infinity, or for large n, okay, reaching the population n, the estimator value it becomes equal to theta. Okay, so as the sample size is increasing, increasing and increasing, the value, the quality of the value, or the distance of the value from the true value, it decreases. Okay, and ultimately it gives us the real best value of the population parameter. Okay, so the bias Bn of theta, it is the difference between the estimated value and the true value. Okay, so if the estimated value and the true value has zero differences, okay, if the difference is equal to 0, it means that it is the perfectly unbiased estimator. But if the estimated value and the true value, okay, so if the estimated value and the true value has zero differences, okay, if the difference is equal to 0, it means that it is the perfectly unbiased estimator. But if the difference between the true value and estimator is not equal to 0, it means that it is biased estimator. Okay, so sometimes what the scenario is that initially for small n, if we are using a small sample size n, okay, it will not hit the exact point, it will not give you the exact value of the population parameter. But as the value of n increases, as the sample size increases, it starts, the distance between the real value and the estimated value, the distance between both of them, it decreases. Okay, and it decreases until the difference is equal to 0, and that is the point when that unbiased the biased estimator becomes unbiased. Okay, so asymptotically unbiased estimator is the estimator which is initially biased, but as the sample size increases, okay, as the sample size increases, that is n tends to infinity, the difference is 0, or the expected value of that estimator is equal to the real value of the population, that is theta. Okay, so for these kind of estimators we call them asymptotically unbiased estimators. Okay, I will repeat it. Okay, asymptotically unbiased estimators are those estimators actually that initially they are biased. Okay, it will not give you the exact true parameter value, but as the sample size n increases, okay, it tends to infinity, it gives you the exact true parameter value. Now I will define the asymptotically unbiased estimators. Okay, so an estimator theta bar is AUE, I will call it AUE in short. Okay, asymptotically unbiased estimator. Okay, if its bias Bn of theta vanishes as sample size n increases to infinity. Okay, mathematically it can be written as limit n tends to infinity Bn of theta is equal to limit n tends to infinity E of theta bar minus theta is equal to 0. It means that as n tends to infinity, the bias of the true estimator is equal to 0. It becomes unbiased. But initially, for small n, there is bias. E of theta bar minus theta, it will give us some value greater than 0. Okay, it means that there is some difference between the real or true parameter value and the estimated value. How to actually interpret this? We can interpret it using an example. Like imagine you are estimating a population mean mu. Okay, you are estimating a population mean mu, based on small sample x1 x2 up to, like for example, x5. You have like 5 sample size. Okay, so as the n, which is a sample size, it improves, you have more data, and when you have more data, you calculate the exact value mu of the population using the x bars. Okay, so both will be kind of equal. When you calculate x bar for large sample, okay, you ultimately get the mean for the population. Or think it like this, like for example, you are shooting arrows at some target. Okay, so in this scenario, an unbiased estimator will be someone who always hit the center of the target. Okay, it never misses. It always gives you the exact point delivery. Okay, but a biased estimator is someone who will consistently fail. Like you have this center. Okay, so for an unbiased, it will always hit the center. For biased, it will hit anywhere near the center, but it will never reach the center. It will never hit the center point. Okay, but the asymptotically unbiased estimator, okay, for that, initially it will hit somewhere off the center, but as it strikes a large number of arrows towards the target, it will ultimately hit the center point. Okay, so that is the interpretation of the asymptotically unbiased estimators. Now I will solve an example on this, and I hope you will understand. Okay, example is like estimating the population mean mu with a biased estimator. Okay, and how to convert this biased estimator into an unbiased one. Okay, so for example, we have the estimator. Okay, we are considering the estimator to be mu n bar. By bar, it means that it is the estimator, or it is the sample mean. Okay, it is equal to 1 divided by n plus 1 summation of I is equal to 1 up to n xi. Okay, this is the estimator. Okay, while xi is where I is equal to 1, 2, 3 up to infinity, these are the sample points. Okay, these are the independent samples from a population whose mean is mu, whose actual mean is mu, and we want to estimate this actual mean mu using this sample sizes. Okay, so the expected value, okay, the expected sample sizes, okay, so the expected value, okay, the expected value of this estimator is equal to the expected value of 1 divided by n plus 1 into summation of I is equal to 1 to n x of I. Okay, now this is constant, the first part. So when we get the expected value of 1 divided by n plus 1, it will give us the exact 1 divided by n plus 1, and the expected value of this I, summation of I is equal to 1 up to 1 xi, okay, it will give us the mean mu. Okay, so it is equal to 1 divided by n plus 1 into mu, which is the expected value of this estimator. Okay, now the expected, for an unbiased estimator, the expected value of this n, it should be mu, but it is not equal to mu. It is equal to 1 divided by n plus 1 into mu, or mu divided by n plus 1. So when it is not equal to mu, it means that it is a biased estimator. Okay, mu n bar, this is a biased estimator, this is not an unbiased estimator. Now we know that the biasness of the estimator Bn of u, it is equal to the expected value of the estimator minus the real value. Okay, now the expected value of this estimator, we know that we got this value for the expected value. So mu divided by n plus 1 minus mu, it is the bias of this estimator. Okay, now taking mu as constant, we get 1 divided by n plus 1 minus 1. Okay, so this is the bias of this estimator. Now when we get the bias of this estimator, we want to get this bias equal to 0. Okay, so let's do that. So let's put mu divided by 1 divided by n plus 1 minus 1 equal to 0. So for what value of n, for what value of n, actually this will be equal to 0. B of n equal to 0. So if this n is equal to infinity, then B of n of mu, it will be equal to 0. So it shows that this bias estimator, okay, it will turn into an unbiased estimator if this n, or the sample size, actually tends to be infinity. For a large, very large sample size, this biased estimator will turn into an unbiased one, and we get our asymptotic unbiased estimator. Okay, so initially we get a biased estimator, but as we can convert it into an unbiased estimator when the sample size becomes large enough up to infinity. Okay, so that is how we get a biased estimator, and we can convert it into an unbiased one, which is the exact definition of this asymptotic unbiased estimators.